We're next going to talk about how adjacent pi bonds, adjacent double bonds and triple bonds, can interact with each other. We're first going to look at a structural feature called conjugation. Conjugation. Conjugation exists when a molecule has alternating pi bond, single bond, pi bond in its structure. So here is a generic example. We have a pi bond in the form of this double bond. Directly attached to that pi bond, we have a single bond, but then directly attached to that single bond is another pi bond. So we're alternating double, single, double. We would say that this is conjugated. In conjugated systems, the p orbitals of the pi bonds can overlap, they can align with each other, and what they can do is they can create orbitals that are larger, that extend over more than just 2 carbons. So for example, in our generic example above, we would have a pi bond here, we would have a single bond, but the adjacent pi bond could line up and we could essentially have an interaction between all of these pi orbitals. This turns out to have several important effects in a molecule. Now, we need to be careful to distinguish between conjugation, where we have alternating pi bond, single bond, pi bond, and cumulation. Cumulation is when pi bonds are directly attached to each other, sharing a carbon in the middle. So here's an example. We have pi attached to this carbon and then another pi bond attached to this carbon. Molecules that have this are called cumulines. The simplest cumuline would be alene, which is this molecule, common name of alene. Cumulines tend to be pretty unstable, very reactive. But again, there are situations and uses for them, although we are not going to study those. Those are mostly advanced organic chemistry reactions. However, I do want to note that in cumulated systems, the p orbitals of the adjacent pi bonds are perpendicular to each other and they can't overlap. So we have this left-hand pi bond being made from one p orbital on the central carbon, but the central carbon has a steric number of only 2, so it's only sp hybridized. So it has a second p orbital, and it's that second p orbital perpendicular to the first that overlaps with the p orbital on the other side to form the second bond. This means that these pi orbitals are completely independent of each other. They don't interact with each other. They don't have any of the effects that we would see for conjugated systems. Well, conjugation has several important consequences. One of the first of which is that conjugation makes a compound more stable than it would be if we just looked at the individual pi bonds by themselves without conjugation. We can see this from I don't know why this didn't reproduce correctly, but it should say delta H of hydrogenation when we look at alkenes and dienes. So this is a diagram of an experiment that I first introduced when we talked about alkenes themselves and the stability of alkenes. We discussed this first in chapter 7 in first semester. In that chapter, we looked at a reaction where we would take an alkene and we would treat it with hydrogen and something like palladium, okay, a metal catalyst. And we would add hydrogen to the double bond, making it into a single bond. And we saw that when we did that, that would be an exothermic reaction and potential energy would be released. And because the product, I'm just going to look at these two first, when we look at these two individual double bonds, because the product would be the same, once you erase or get rid of this double bond, it just becomes a 5-carbon chain. The product would end up with exactly the same amount of potential energy. So therefore, if there's a difference in the amount of potential energy released, that difference reflects a difference in the potential energy of the reactant. So if we go down less, we must have started up less high. When we go down further, we must be starting up higher. So we took home some lessons from this last semester. For example, we saw that the more carbon groups attached to a double bond, the lower its potential energy, the more stable it would be. We also saw that trans double bonds were more stable than cis double bonds. And so all of that probably makes these numbers not surprising. The mono-substituted 1-pentene has a higher potential energy than the di-substituted trans 2-pentene. Notice also that when I made this diagram, I made it with the old IUPAC nomenclature system. I guess I'm ultimately going to have to update this. Now, what we could do then is we could imagine taking this molecule with a double bond and then adding another double bond all the way on the other end, not conjugated, so that they were what we would call isolated double bonds. That would create this structure. If we then completely hydrogenate this molecule, it would also become pentane. It turns out when we do this, what we see is that each double bond releases about 30 kilocalories per mole of energy when it is hydrogenated, and since there's two, it just adds up pretty much directly, and we get about 60 kilocalories total energy released when we have done both of the double bonds. So in other words, these numbers should be more or less additive. Now, when we move this double bond into conjugation, you can see that it is no longer a mono-substituted double bond. It is, in fact, a di-substituted trans double bond. So we would, first of all, expect this molecule to have a lower potential energy, to release less energy, just because instead of being 2 times 30, the energy released should be 30 plus 27. 30 for this one, 27 for this one. That number is represented right here with this dotted line. It turns out when we actually do this experiment, the amount of potential energy released is actually almost 4 kilocalories lower than we expect. So 30 plus 27 is 57.4 kilocalories. Instead, we actually get only 53.7 kilocalories. We then have concluded that this 3.7 kilocalorie difference, more or less, is caused by the fact that those double bonds are conjugated to each other. It's an additional stability, an additional reduction in potential energy caused by conjugation. We see this effect in many circumstances, in many different ways, when we look at conjugated molecules. One consequence of this, then, is that conjugated products can break Zaitsev's rule. Here's an example. So this molecule, if you look carefully, it's got a phenyl group, a CH2, a CHBr, and then a CH with 2 methyl groups attached. Okay? The phenyl group itself already has pi bonds and is conjugated. And in fact, it has a pi bond here adjacent to this single bond. And then if we form another pi bond, that would also be conjugated. So if we do E2 elimination on this reaction, and we just work through the way we always have, We locate our alpha carbon. We look at all the possible betas. So we have beta 2 on this side, beta 1 on that side. And we're using a non-sterically hindered base. We would actually expect that beta 2 hydrogen would be the preferred hydrogen to remove. That's because, following Zaitsev's rule, we generally prefer to remove the hydrogen from the more substituted carbon. So this is a tertiary carbon, this is only a secondary carbon. The tertiary hydrogen should be removed. Actually, when I did these notes, I sort of did this backwards. I should have shown this one first, right? But here we are, alpha, double bond, beta 2. We would call this the Zaitsev product. We would also notice that it is tri-substituted. Zaitsev said we prefer to make the double bond, which is more highly substituted, and normally we would prefer this one. However, we also have, as a possible product, the product coming from removing the beta hydrogen 1. That would create this product where we would go alpha to beta 1, and then we would have the phenyl group. If we look at this product, alpha to beta 1 is a pi bond, we have a single bond, and then we have conjugation in with the phenyl group. So this product would be conjugated, although the double bond itself would only be di-substituted. It turns out that in this case, the conjugated product, against Zaitsev's rule, is actually the preferred product, because conjugation adds more stability than just adding additional carbon groups. We're also going to look at how conjugated dienes can react a little bit differently in our normal diene reactions. We are going to limit ourselves in this case to only the diene reactions, the alkene reactions where we directly add a hydrogen and then a nucleophile. So we have hydrogen halide addition under cations. We have acidic hydration, acid catalyzed hydration. There are more complicated issues going on when we use other reagents like Br2 or borane or things like that. So we're going to use hydrogen halide, where the halide would be chlorine, bromine, or iodine, and we would have no peroxide. In that case, if we looked at this molecule right here, which is the smallest conjugated molecule we would have, we call this buta-1,3-diene, or sometimes just butadiene. In this case, what we can see is that if we add hydrogen halide, one equivalent so that we're only adding it once, we would expect one or the other of the double bonds to react. The double bond would go away. We would follow Markovnikov's rule and add hydrogen to the side with the most hydrogens already attached, and we would add the halogen to the other side. We call this the 1-2 product. 1-2 is really relative numbering. What we do is we basically start at one end of the conjugated diene system and we say 1, 2, 3, 4 to the other end. So in the 1-2 product, we've reacted or added atoms to carbon 1 and carbon 2 of the 4-carbon system. In this case, that also corresponds to 1 and 2 of the actual molecule for IUPAC numbering, but with relative numbering, it's not always the case. This, therefore, forming the 1-2 product is called the 1-2 addition. However, it turns out we get another product. In that product, the other double bond, which hasn't reacted, has shifted over toward carbon 1. And we've added a hydrogen on carbon 1, but we've added the halogen or other nucleophile to carbon 4. This is called the 1,4 product. When we actually do the reaction, we generally get a mixture of these two products. Why do we get these two products? Well, again, this is caused by allylic resonance of the carbocation intermediate. So if we imagine that we start with our butadiene and the pair of electrons from the double bond between carbon 1 and 2 comes out and makes a bond to the hydrogen, pushes out the halide, and forms this carbocation. This carbocation is an allylic carbocation. So what we know is that the allylic pi bond can shift toward the empty space in the carbocation. That creates a pi bond in a different location and an empty space on the end. Again, now we have two resonance structures of our intermediate. The next step for our reaction would be for the halide that was formed to be attracted to, in an SN1-like reaction, the empty space on the carbocation and use its pair of electrons to make a bond to that carbon. However, in our allylic carbocation, we have some percentage of carbocation partial positive here, but we also have some percentage of carbocation partial positive there, which can also attract the nucleophile. So some percentage of the time it plugs in here and we get the 1,2 product, but some other amount of the time it plugs in on carbon 4 with the double bond shifted and we get the 1,4 product. So we get a mixture.